Hello guys, welcome to week 12 of Math 120. We've been talking about hypothesis tests, and last week all of hype tests that we did were for categorical data. In other words, for proportions. We did tests to answer, do we have evidence that the proportion is bigger than we think it is, or smaller, etc., etc. This week, we're going to do the same technique, but for quantitative data. So in particular, we'll be asking questions about means. Do we think the mean is bigger? Do we think the mean is smaller? Etc., etc. Keep in mind, these symbols are really important since they all appear in the problem at the same time. Last time, we were saying smart things about p based on p hat. This time, we're going to be saying smart things about mu based on x bar. So let's see some examples. Let's just dive in with an example and think about what's going on here. So for example 1, this first paragraph is the problem itself. It says the height for adult men ages 20 to 29 in the United States is 69 inches, in other words, 5'9". However, a researcher suspects that male students at Denison have a higher average height than the general population. Right there. We know that for all men in the United States, the average is 69 inches. But what if we suspect for this population, male students at Denison, maybe we think that that average is higher for some reason? And to investigate this suspicion that we have, we take a random sample of 40 men at Denison. And in this sample, we find an average height of 70.2 inches with a standard deviation of 3.4 inches. And that's the stuff that we're calculating from our spreadsheet or R or whatever. The question is, does this sample provide evidence to support the researcher's suspicion? We're going to do a hype test. Before we jump in, I just want to make a few important observations about what's going on and what we hope to do here. This hypothesis test, just like any, is a question about a population. We're asking a question about a population. That's what hypothesis tests do. In particular, here, the question that we're asking is the mean height, mu, for male Denison students larger than 69 inches? That's the question we're asking. And just like in any hypothesis test, we've got some sample data. We're going to use that sample data to answer the question. Now, if you look at the sample data too, the sample data had an average of 70.2 inches. So certainly the sample average is higher than 69. That's not in question. It's clear here that this sample data was a higher mean than 69 inches. It's 70.2. But we know that it's just a random sample. And we wonder, does that provide strong evidence that the whole population mean is larger than 69? And that's what this test is designed to show. What sort of evidence do we find in this sample? And one last thing, I think it's super helpful for students in these problems. The alternate hypothesis is always clearly stated. In this one, we wonder if the mean is bigger than 69. So that's it right there. The alternate hypothesis always has to be in the problem. So you know then what the hypotheses are going to be. That means you know the null hypothesis also, because the null hypothesis is always a statement of equality. The null hypothesis always has to say equals. Okay, So with those preliminaries out of the way, let's do this test. First, hypotheses. Well, our alternate hypothesis, I'm just going to copy paste this because we've got this already. We wonder if the mean is bigger than 69. That's the whole point of the test. That means our null hypothesis has to be that mu is equal to 69. The null hypothesis is always a statement of equality. It's the logical opposite of the alternate hypothesis. Okay, so let's get our test statistic. This is our first test for means. So I'm going to take this one slow. Remember, every test statistic is basically a z-score. So our test stat here, just like always, it's going to be a fraction. On top, it's observed minus expected. And on the bottom, it's the standard deviation. Here, we're talking about means. So let's break these pieces down. Our observed for this stuff is x bar, the sample mean. That's what we actually saw in our data. And the problem says that that was 70.2 inches tall. Okay, what about for our expected? For the expected, remember, hopefully this is starting to seem familiar. This is just like with confidence intervals. It's just like with the sampling distribution problems that we did. Our expectation for means is the population mean mu. And, oh, I forgot, what is it, 3.4? You can see it's right here. I'm getting this information from the sample. 3.4. Oh, no. I'm sorry. I just totally misspoke there. I apologize. Our expectation is the thing that comes from the null hypothesis. Got a little bit ahead of myself. I'm sorry. I better write that. Note. Expectation always comes from H naught. We always know what the expected value is from H naught. I'm sorry, I misspoke a second ago. So let's fix that. 69. That's our prior assumption here. That's what the null hypothesis says is going on. We're going to make the assumption that it's 69. We're looking for evidence otherwise. And our standard deviation, we're talking about means here. So we're going to use s divided by the square root of n. Talking about means, so we're using this formula. Maybe one note here, note, only have sample standard deviation, s. So use the t-table, not the z-table. And that's just the same as last week when we did confidence intervals for mu. If you want a little refresher on how the t-distribution works, go back to the week 10 notes, and take a look at the t-table stuff. We'll practice more in these notes too. Here, for this one, the standard deviation is 3.4, and our sample size is 40. So we've got 3.4 divided by the square root of 40. Cool. That's everything we need. Let's stick it all into our calculator and find out the test statistic. Observed is 70.2, expected is 69, and the standard error here is 3.4 over the square root of 40. One little note about this, all of these parentheses are totally necessary. You need all of these parentheses that I'm using right now. Otherwise, the order of operations is wrong. We just got a test statistic of 2.23. Cool. So let's look at our p-value. And I'm going to put a note in here, again, kind of repeating myself. Note, use t-table for means. Use z-table for proportions. They're very similar, but the t-table accounts for the fact that we don't know what the population standard deviation is. So it does work a little bit differently. I'm going to do it in a second. This is a new skill. Warning, danger, new skill. Here's the thing that you haven't done before. Let's take a look at the t-table to find out what our p-value is. And remember, p-value is tail area. I'm going to come over to the t-table now. One thing I'm going to remind you guys, let's see. Here's our book. Let's see my progress. Table of contents, distribution tables, and here is the t-table. Remember that the t-distribution depends on degrees of freedom. So we need to think about what the degrees of freedom are before we can use the table. On this problem, our sample size was 40. Sample size is 40. So our degrees of freedom here, df, it's n minus 1. And of course, that's just 40 minus 1, or in other words, 39. We're going to be using degrees of freedom 39. Degrees of freedom is basically the same thing as sample size. All right, so let's check out the table. Coming to degrees of freedom 39, it's here. Here's the row. Here's where it works a little bit differently than the z-table. We got a test statistic of, what was it, 2.23? We got a test statistic of 2.23. So our test statistic is somewhere in between these two. Do you see that? Degrees of freedom is 39. Our test statistic is bigger than 2.02. It's smaller than 2.43. So it lives somewhere in here. Okay. That's the test statistic, but what about the p-value? On the t-table, the tail area is actually shown up above. It's this margin up here on the top. It says one tail or two tail. We're looking for our tail area, and that means it has to be between 0.025 and 0.01. We don't know exactly what our p-value is, but we know it's somewhere between those two. Let me just write that down. From the table, we see that our p-val was it between 0.01 and 0.025? It's got to be somewhere between 0.01 and 0.025. Let me talk through that one more time, just in case you missed. Degrees of freedom is 39. The test statistic is between 2.02 and 2.43 here. Our test statistic lives somewhere in here. And that means that the tail area is somewhere between these two, 0.01 and 0.025. We don't know exactly what the p-value is, but that's okay. That's enough for us to make the conclusion. In this case, we've got a small p-value. Let's make our conclusion. since alpha not stated, we're going to use alpha equals 0.05. Just making that clear. You don't have to say that, but this problem didn't specify a specific value for alpha. We'll assume it's 0.05 by default. So, question, is our p-val smaller than alpha? The answer is yes. Here, we know that the p-val is definitely less than 0.025. I don't know exactly what it is, but I can see that it's definitely smaller than 0.025. So that means our p-val has to be less than 0.05. How about alpha? i.e., our p-val is small. We've got a small p-value here. So we're going to do what we always do when we have a small p-value. Thus, we reject the null hypothesis. And that means there's strong evidence that the troop mean height of men at Denison is greater than 69 inches. The end. That's the hypothesis test. We have found, based on the sample data, statistically significant evidence that male students at Denison are taller than the national average of 69 inches. Now, I just made up this data, so I'm not sure if that's really true. But that's how the test works. There's one detail in this problem that might seem a little bit weird. Don't worry, I'm going to do a couple of these. It was here when I read the table. I didn't say too much about it at the time, but I looked at the one-tail area for this, and if you've used the t-table so far, you might have wondered a little bit about the one-tail versus two-tail stuff. Let's talk a little bit more about that for hypothesis tests. That's our next topic. One-tail versus two-tail tests. In other words, left tail or right tail or two-tail tests. To understand what's going on here, you need to remember the definition of what a p-value is. What's the definition of p-value? If we still had essay questions, I would ask you this as an essay question. The p-value is the probability of observing a sample result that's as or more extreme than the one we got, assuming that the null hypothesis is true. And right now, I want to focus on this part, as or more extreme. What does that mean? What does it mean to be more extreme? The answer is it depends on what we're trying to show. And there's three possibilities. They all depend on the alternate hypothesis. Remember, the alternate hypothesis is always a statement of inequality. Null hypothesis has equals, always. The alternate hypothesis either has greater than, less than, or not equal to. If we're doing, if we think it's smaller, if we think the parameter in question is smaller than the status quo, then we've got less than in our alternate hypothesis. And that means we're looking at the left tail. Our notion of extreme in that case is small. We're going to get convinced by a small sample result. On the other hand, if we've got greater than in the alternate hypothesis, then that means our notion of extreme is larger. We're looking for a big sample result in order to convince us. that were correct. That's a right tail test. There's one other option that's new for us in this class that we haven't done yet. Instead of less than or greater than, we could just have not equals to. So in that case, we don't specifically think less than or greater than. We don't specifically think smaller or bigger. Instead, that means our tail area could be on either side. It could be on both sides. My head is a normal curve again, and the tails are out here. If we're testing for not equals to, the tail area could be either on the left or on the right. Either one of those would make us think not equals to. So we want to include both of them in the p-value. Let's look at a picture. I think that this picture explains what's going on. Here's a picture I found from the internet. This shows the total breakdown for all the possible options. You can see the only thing that matters is what's going on in the alternate hypothesis. That's our claim about the population. If we're doing a test to show that it's bigger than, the p-value is the area over on the right side. That's a one-tail test because it's just the one tail over on the right side. Left tail tests are the same thing, but for less than. If we think smaller than, then we've only got one tail. We're going to look on the left. Fortunately, it doesn't matter too much which tail we're looking at. They're both going to have the same area because it's symmetrical on both sides. But if we've got a two-tail test, not equals to, then in that case, we want to think about the tail area on both sides. We don't just want the bottom one, we want the upper one also, and vice versa. This picture explains everything for the p-value. The red shaded area is literally a visual representation of the p-value. Now, practically speaking, this doesn't really make things too hard for us. It's pretty easy for us to find the area. If it's a one-tail test, find the area of the tail and you're done. If it's a two-tail test, no worries. Just multiply it by 2. That's it. That's all you got to do. It's symmetric on both sides. The left tail and the right tail always have the same size. So if you're doing a two-tail test, just use both of them times 2. And that's all there is to it. You can see, let me show you again, check this out. You can see in the table, I think it's almost kind of stupid that they include both of these, because look, the one tail is 0.1, two tail is 0.2. If the one tail is 0.05, then the two tail is twice as much, twice as much, twice as much. It's literally just times 2. Look at that. Once you realize that, I think it's almost kind of silly that they include both of these things on the table. Maybe if you haven't had enough coffee, it's difficult to multiply by 2. But that's what it's for. It's just literally showing you if the left and right tails have an area of, if the left and right tails have an area of 0.1, then of course the two tails together have an area of 0.2. Not a mystery. That's all that those things are showing there. And to decide which one is the right one to look at, it's easy. It's super, super easy. All you got to do is look at the alternate hypothesis. If the alternate hypothesis is not equals to two-tail. If it's either less than or greater than, those are both going to be one-tail. It doesn't matter if it's on the left or the right. It's the same area on both sides. That's why here on the table, for the one tail, it doesn't specify if it's on the left or the right. You can see on the picture, it doesn't matter. Those are exactly the same area. Let me show you an example that can hopefully clarify this. This is going to be another example with means. It's an important example because we've only done one so far. This is going to be the second example with mu. And it's also going to be a two-tailed example. I'll show you how that works. All right, here's example 2. In this one, we're talking about IQ. And this is true. The mean IQ for the general population is 100. And they actually do constantly tweak the test every year to ensure that that's the same. Suppose that a researcher suspects that professional musicians have a different mean IQ than the general population. Before we get into any math, think about this for a second. It's a reasonable suspicion. Maybe you think this particular population is different. Maybe playing music changes your brain. I am not a professional musician. I listen to Spotify a lot, but I can't play any instruments. So there's no pride in this question. But it's a thing people wonder. Maybe playing music changes your brain somehow. Maybe it makes you smarter. Maybe it makes you less smarter. The question that we're wondering here is, do we have evidence of a different mean IQ? And that's really important. That word different there right away tells us the alternate hypothesis. Since we're looking for difference, not necessarily greater than or smaller than, our alternate hypothesis is going to be not equals to. Let me write that right now. Our alternate hypothesis, mu not equal to 100. We think it's different than 100. Not necessarily smaller, not necessarily bigger, just different. Of course, for the null hypothesis, right away, that means mu has to be equal to 100. Those things always have to be logical opposites of each other. All right, well, let's take a look at the data and see if we've got support for this. To investigate this suspicion, our researcher administers an IQ test to 55 randomly selected professional musicians. From this, a mean IQ, from the sample data, we compute a mean IQ of 103.2, standard deviation of 9.2. Does this sample data provide strong evidence to support our suspicion? We've already got the hypotheses ready, so let's finish the rest of the test. Our test statistic on this one is going to be just like last time. Maybe to express it and yet, to make it as clear as possible. If we're talking about means, the test statistic is x bar minus mu divided by s over the square root of n. That's observed minus expected divided by the standard deviation for the sampling distribution. So here on this one, our observed was 103.2. Standard deviation is 9.2. Sorry, I'm really excited to use that standard deviation today. Our mu, it says right here, pardon me, our mu right there is 100. Standard deviation is 9.2. And our sample size on this one is 55. So we've got a test statistic here of 2.579, but let's say t equals 2.58. Okay. Let's take a look at the table to see what the p-value is. Remember on this one, since we've got not equals to in the alternate hypothesis, we're going to be looking at the two-tail area for this stuff. And remember our degrees of freedom here, that's 55 minus 1, in other words, 54. So let's look at the table. Degrees of freedom, here's one where 54 isn't exactly on the table. It just goes from 50 to 60. If you're ever in that situation, use the next smallest one. We're going to use use df equals 50, since 54 isn't on the table. It's not a really big deal either way. You can see they're pretty close to each other. They only differ by a tiny amount. But use the next smallest one. That's the best practice. It's more conservative. Our test statistic was 2.58. So that's between these two. Our test statistic is between 2.4 and 2.68. Do you see where my mouse cursor is? It's between those two right there. That's where I'm looking at on the table. All right, let's look up above for the p-value. The p-value is going to be up here. Do you see my mouse cursor? I'm going to be looking at the two-tail version of this because it's a two-tailed test. And that puts our p-value somewhere between these two. Oops. Somewhere between 0.02 and 0.01. Our p-value is between 0.02 and 0.01. From the table, our p-value is between 0.02 and 0.01. We don't know exactly where in there our p-value is, but that's okay. It's still enough information for us to do the test. By the way, in R, the command is really easy if you want to find the exact p-value. The exact p-value for this stuff. Oops, 2 times. Sorry, this may not seem super easy. If you want to play around, here's the exact p-value. The exact p-value for this stuff is 0.012, which is indeed between 0.01 and 0.2. But this is still enough information for us to make the conclusion. Looks like we've got a small p-value here again. In our conclusion, since p is less than 0.05, we reject. The null hypothesis, there's strong evidence. What did we find strong evidence of? Oh yeah, that the mean IQ of musicians, professional musicians, differs from 100. The end. So this hypothesis test that we just did, totally the same thing as the ones we've seen previously. A little additional wrinkle here is the fact that we're using a two-tail p-value because of the not equals to in the alternate hypothesis. I've got one more example for you guys about proportions, but I think this video is probably getting long enough, so I'm going to stop this one here. Let me show you next time when we continue a similar example. It's also going to be a two-tailed test because of that word right there. But it's about proportion because we're talking about sex ratios here. Okay, cool. Oh, look at me. Here I am forgetting the secret question again. What's our secret video question for today? The secret video question for week 12 video 1 is green tea, which is sitting off camera right over there, but I can't reach it. Green tea. Green tea. I love green tea. Green tea is the answer to the secret video question for week 12 video 1. Green tea. Okay guys, see you next video.